Good morning, guys. Let's start with Laplace transforms. Laplace transform is widely used by engineers and scientists, and many research problems end up with ordinary differential equations subject to a set of initial conditions or boundary conditions. These type of problems are referred as initial value problems and boundary value problems respectively. One of the methods used to solve these type of problems, that is IVPs and BVPs, is Laplace transform. So this is all about the introduction and application of Laplace transform. Moving on to the definition part of it, let f of t be a real value function defined for 0 less than or equal to t less than infinity. This is the interval for t. Then the Laplace transform of f of t denoted by L of f of t is defined by integral 0 to infinity e power minus st ft dt provided the integral exists, where s is the real or complex number called as Laplace transform parameter. From equation 1, that is from the definition of Laplace transform, it is clear that L of f of t is a function of s. See, once we integrate this with respect to t, the resultant will be a function of s. And this function is denoted by f of s, capital F of s or small f bar of s. And this capital L is called as Laplace transform of operator. And if L of f of t is capital F of s, that's equal to f bar of s, then f of t is equal to L inverse of f of s or L inverse of f bar of s, and is called inverse Laplace transform. And this L inverse is called inverse Laplace transform operator. Let's move on to basic properties of Laplace transform. First one is the linearity property. For any two functions f of t and g of t, and any two constants c1 and c2, Laplace transform of c1 into f of t plus or minus c2 into g of t is equal to c1 into Laplace transform of f of t plus or minus c2 into Laplace transform of g of t. So to prove this, I will use the definition of Laplace transform, that is L of f of t is equal to integral 0 to infinity e power minus st ft dt. So in place of f of t, I am having this function c1 ft plus c2 gt. So 0 to infinity e power minus st, in place of f of t I am writing this whole function. So Laplace transform of this is equal to integral 0 to infinity e power minus st into c1 f of t plus c2 g of t into dt. In next step, what I'll do is I'll split the integral and I'll take this constant c1 and c2 outside the integral after splitting. So that looks like this: c1 into integral 0 to infinity e power minus st ft dt plus c2 into integral 0 to infinity e power minus st gt dt. c1 into this integral can be written as Laplace transform of ft plus c2 into this integral can be written as Laplace transform of gt. So similarly, this can be written for subtraction also. So the same proof follows for subtraction also. And moving to the next property, First shifting property. This states that if L of f of t is equal to f of s, capital F of s, then L of e power at ft is equal to f of s minus a. So if we multiply this f of t with some exponential function e power at, then its Laplace transform is changed by this thing. This function of s becomes function of s minus a, where a is the coefficient of t in this exponential. So from the definition of Laplace transform, we have f of s is equal to 0 to infinity e power minus st ft dt. So what is f of s minus a? F of s minus a is equal to, see, in place of s I am having s minus a. So here also in place of s I will be having s minus a. And the remaining thing will be unaltered. E power minus of s minus a into t f of t dt is equal to integral 0 to infinity. I have split this using the law of indices, e power minus st into minus into minus is plus at. So e power at ft dt. So in place of f of t I am having e power at ft and remaining thing the same. So in place of ft I have e power at ft. So this can be written as Laplace transform of e power at ft. So I have proved this. F of s minus a is Laplace transform of e power at ft. Now let's solve some standard functions for Laplace transform. First one, Laplace transform of a constant function a, L of a. L of a is equal to, by using the definition of Laplace transform, 0 to infinity e power minus st, ft here is a dt. I have taken that a outside the integral, and integration of this e power minus st is e power minus st by minus s between the limit 0 and infinity. Applying the upper limit, I have e power minus infinity equal to 0 and e power 0 equal to 1. I have taken this minus s outside as it is a constant, so minus a by s into 0 minus 1 is a by s. So Laplace transform of a is equal to a by s. Second one, Laplace transform of e power at. So using the definition of Laplace transform, I have integral 0 to infinity e power minus st e power at dt is equal to, again using the law of indices, I have written like this, into dt, and integrating this exponential with respect to t, I have e power minus of s minus a into t divided by minus of s minus a between the limits 0 and infinity. So when I use the upper limit, it is 0, e power minus infinity 0, minus of minus e power 0 is 1 divided by s minus a. So minus into minus will be plus 1 by s minus a is the Laplace transform of e power at. Going to the third one, Laplace transform of t power n. Using the definition of Laplace transform, I have 0 to infinity e power minus st t power n dt, and I've used the substitution method to solve this integral. So I have taken this st as x, and when I differentiate that, I have s into dt equal to dx, or dt is equal to dx by s. And these limits are for t. Now I want the limits for x. So when t varies from 0 to infinity, when t is 0, x is 0, and when t is infinity, x is infinity. So x also varies from 0 to infinity. So using all these in this integration, I have Laplace transform of t power n is equal to integration of e power minus x, because st here I have taken as x and t is x by s to the power n, and dt is dx by s between the limits 0 and infinity. So here I have taken this constant s outside the integral. So s power n and s is 1 by s power n plus 1. Taken that outside, 0 to infinity, e power minus x power n into dx. So I left with this one. And this is nothing but the gamma function. This is actually the definition for gamma function. That is gamma n plus 1 divided by s power n plus 1. And also I have alternate method to solve this Laplace transform of t power n, that is by parts. This was by substitution method, and next alternate method by parts. Here I have taken this exponential term for integration and this polynomial term for differentiation. So by parts I have t power n into integration of this e power minus st, that is e power minus st by minus s between the limit 0 to infinity, minus integral of this integration t power minus st by minus s into derivative of this t power n into t power n minus 1 dt. And when you apply the upper limit, e power minus infinity is 0, and when you apply the lower limit, 0 power n is 0. So this whole term vanishes. And moving on to the second term, minus into minus is plus. And when you take this constant term n by s outside, you are left with integral 0 to infinity e power minus st t power n minus 1 dt, which is nothing but the Laplace transform of t power n minus 1. So this integral, when you see, is actually the Laplace transform of t power n minus 1. So n by s into Laplace transform of t power n minus 1. So what is Laplace transform of t power n? It is n by s into Laplace transform of t power n minus 1. Similarly, using this, I can write for Laplace transform of t power n minus 1. So that is n minus 1 by s into Laplace transform of t power n minus 2. Similarly, I can write it for Laplace of t power n minus 2. That is n minus 2 by s into Laplace transform of t power n minus 3. So, and so on. Using all these results, I can write Laplace transform of t power n equal to n by s into Laplace transform of t power n minus 1. And Laplace transform of t power n minus 1 is n minus 1 by s into this. And this is n minus 2 by s into n minus 2 by s into this. And so when I continue this now, this will go up to 2 by s into Laplace transform of t, or 1 by s into Laplace transform of t power 0. So at last, this t power 0 is nothing but 1. Laplace transform of 1 is 1 by s. And this remaining things here, n into n minus 1 into n minus 2, etc. 2 into 1 can be written as n factorial. And there are n times s here. So I have written that as s power n. And this 1 by s is for Laplace transform of 1. So finally, I'll be arriving at n factorial by s power n plus 1. So this is all about Laplace transform of t power n. So the one formula is Laplace transform of t power n is gamma n plus 1 by s power n plus 1, or n factorial by s power n plus 1. Moving on to the next transform, cos hyperbolic at. Laplace transform of cos hyperbolic at. Here I have written this cos hyperbolic at in exponential form. E power at plus e power minus at divided by 2. And I have taken that by 2, 1 by 2 outside, since it's a constant. And I have used the property of linearity. L of e power at plus L of e power minus at. I know what is Laplace transform of e power at. That is 1 by s minus a. So it is 1 by s minus a. And Laplace transform of e power minus at. See here, in place of a, I am having minus a. So when I replace this a by minus a, I'll be having s plus a. So I've written the same here, 1 by s plus a for this Laplace transform of e power minus at. When I take the LCM, I have s plus a plus s minus a divided by s minus a into s plus a. Plus a and minus a will get cancelled and I'm left with 2s. 2 will get cancelled and I'm left with s by s square minus a square, and that's the Laplace transform of cos hyperbolic at. And this, let's move on to transform of sine hyperbolic at. Here also I have written the exponential form of sine hyperbolic at, that is e power at minus e power minus at divided by 2. I have taken half outside as it's a constant, and again I have applied the property of linearity. L of e power at minus L of e power minus at. So L of e power at is 1 by s minus a and L of e power minus at is 1 by s plus a, with a minus sign here. And when I take LCM, I have 2a, because this s and a minus s will get cancelled, and I have 2a by s square minus a square. 2 will get cancelled and I have left with a by s square minus a square. That's the Laplace transform of sine hyperbolic at. Moving on to the next transform, transform of cos at. Laplace transform of cos at is equal to, I will use the definition of Laplace transform, integral 0 to infinity e power minus st cos at dt. And I know the formula for this integral. Integral e power at cos dt is equal to e power at by a square plus b square into a cos bt plus b sin dt. In place of a, I am having minus s, and in place of b, I am having a. So, Laplace transform of cos at is equal to e power minus st by minus s whole square plus a square minus s cos at plus a sin at between the limits 0 and infinity. I have taken this constant s square plus a square outside. 1 by s square plus a square into, when I apply the upper limit, infinity, e power minus infinity is 0 minus e power 0 into minus s cos 0 plus a sin 0. Sin 0 is 0, cos 0 is 1. So this is minus 1 into minus s, which is equal to plus s by s square plus a square. Moving on to the next transform of sin at, Laplace transform of sin at is equal to, using the definition of Laplace transform, I have 0 to infinity e power minus st sin at dt. Formula for this integral is e power at divided by a square plus b square into a sin bt minus b cos bt. So Laplace transform of sin at is equal to, see here also in place of a, I have minuses, and in place of b, I have a. So e power minus st divided by minus s whole square plus a square into minus s sin at minus a cos at 0 to infinity. Again, I have taken this constant outside and I have taken this minus outside. So it is minus 1 by s square plus a square into e power minus st s sin at plus a cos at between the limits 0 to infinity. When I take the upper limit, it is 0, and when I take the lower limit, it is 1 into s sin 0 is 0 and a cos 0 is a minus a. So that becomes a by s square plus a square. And this is the Laplace transform of sin at. And by using the fast shifting property, that is if L of f of t is equal to f of s, then L of e power at f of t is equal to f of s minus a. So We are using this in the below results. So L of e power at t power n is equal to so much. See here, we know L of, that is Laplace transform of t power n, is n factorial by s power n plus 1. So in place of s, I want to replace s minus a because of this term. See here, in place of s, I have s minus a. When there is this exponential e power at with this f of t, I will replace s by s minus a. So Laplace transform of t power n is n factorial by s power n plus 1. And because of this e power at here with this t power n, I will be replacing s by s minus a. So s power n plus 1 will become s minus a power n plus 1. Similarly, the remaining. See, Laplace transform of cos bt is s by s square plus b square. But there is e power at here, and I'll replace s by s minus a. So s minus a by s minus a whole square plus b square. And we know that Laplace transform of sin bt is b by s square plus b square. And wherever there is s, I am replacing it by s minus a. So it is s minus a whole square plus b square. And similarly for cos hyperbolic bt and sin hyperbolic bt, see, Laplace transform of cos hyperbolic bt is s by s square minus b square. So since there is e power at extra here, I'll be replacing s by s minus a. Therefore s minus a by s minus a whole square minus b square. And here e power at sin hyperbolic bt is equal to, see, Laplace transform of sin hyperbolic bt is b by s square minus b square. And therefore Laplace transform of e power at sin hyperbolic bt is b by s minus a whole square minus, sorry, this is minus, please change it, minus b square. So this is all about the standard functions, and we'll move on to the problems in next video. Thank you.